Oh, you're seeing the results coming in on your end.
Yeah.
Okay, good.
Yeah,
Just
I see
checking.
the results. So we're like 83% public health people and 7% IAQ people and a bunch of others. Interesting. All right, looks like that's done. So can people see the results at this point? Yeah, okay, cool. All righty, so do I just hit stop sharing? How do you get rid of the poll, Leah?
I think it's done now.
Okay.
I think people can just close it on there. They can just close it.
Okay.
I've stopped sharing. They can close it.
Awesome. Okay. So we're mostly public health people with a smattering of others. But as I said, this is kind of targeted to a wide audience. If you haven't been to an NCCEH seminar before, you should know that we are just one of 6 what are called national collaborating centers, which are scattered across Canada. We were established by the Public Health Agency of Canada in 2005 in response to the first SARS pandemic. And since then, we've just been chugging away, identifying knowledge gaps, synthesizing the evidence, and otherwise supporting environmental public health professionals across Canada and sometimes internationally as it happens. So today, super quickly, I'm going to be talking about a little bit of background about why we were interested in DIY air cleaners. We'll talk about how those air cleaners compare to commercially available units. We'll talk about how DIY devices have been deployed in the real world, how to choose a design and build it well, how to do a little bit of maybe quality control, safely operating these suckers, and some very pesky limitations that a lot of people don't want to deal with, but we have to acknowledge because there's some pretty serious limitations here. And then we'll sum up. So just to get started, DIY air cleaners have been around for quite some time. They're pretty widely recommended by public health and other agencies to protect people against wildfire smoke. So they've become kind of like a key, like emergency, there's a fire, all the air cleaners at the Canadian Tire sold out. So here's what you can do instead to protect yourself, especially if you are part of a vulnerable population that has some respiratory health problems to begin with. However, during COVID, there has been a surge in interest around air cleaners as a supplement to ventilation. And that's a great thing because that meant that there's now been a whole bunch of new research, which means that somebody like me can turn around and do an evidence review on them. So silver lining. So the key thing about these DIY air cleaners is that they are made of very inexpensive, widely available materials, and they can be assembled quickly and installed just by plugging them in. And you don't need any kind of building permit or renovations or modifications of any kind. They're just a plug and play solution to an air quality problem. Okay, but as public health people, obviously we want to know, do these things work? Do these DIY air cleaners work as well as the commercial units? If we're going to be recommending them to people to use them, to rely on them. So just so you know, commercial portable air cleaners, I'm not talking about, like central HVAC filtration, but just the portable air cleaners, the commercial ones that you can buy at a hardware store, they contain at least a HEPA filter that removes 99.97% of particles in the smallest size range that we measure, which is 0.3 to 1 microns. And they do that removal in a single pass. So the air passes through once, it removes 99.97% of those tiny particles. And these commercial air cleaners often have a bunch of other bells and whistles. So they might have a carbon filter, they might have photocatalytic oxidation, they might have a sensor that tells you when the filter is starting to get clogged up, stuff like that. But because of that, they're a little bit pricey. So depending where you are in Canada, for a good one of these air cleaners, you're going to be paying a couple $100 to $500 for a good one. You can get cheaper ones, but they maybe have a really, really low capacity to clean a space, like they for a very small space. We'll talk a bit more about that. So the DIY versions are so much cheaper because they are simply just a box fan, a big 20 by 20 inch box fan, and a MERV 13 furnace filter, which run about $15 here in Canada. So these MERV 13 filters, they have much lower filtration efficiency, like about 50% instead of 99.97 on a single pass of air through the filter. But they're still going to remove some of the PM. And the idea, the particulate matter, which is PM, The idea here is that if you just increase the airflow or you increase the filter area, that's going to help make up for some of that lower filtration efficiency. So you'll still be able to get a good clean air delivery rate, even with this lower efficiency filter. So how do we measure effectiveness in an air cleaner? So we do that by determining this thing called the clean air delivery rate, which is it's a measurement of in a chamber with like under very controlled circumstances, how quickly that air cleaner can remove particulate matter from the air compared to just natural decay or settling or dissipation alone. So that's what we call the clean air delivery rate, the CADR, the CADR is my short way of calling it. So commercial devices that you buy at the store are evaluated by this group called the Association of Home Appliance Manufacturers, AHAM, and they're evaluated over several different particle size ranges. So right here, you'll see there's a clean air delivery rate for tobacco smoke, which is the smallest particle. There's one for dust, which is bigger, and then there's one for pollen, which are the biggest particle, or an example of some of the bigger particles that they'll filter out. So when you choose one of these devices, first of all, it should have some sort of like mark on it that it's been certified or evaluated. And then the smoke counter, so this, I don't know if you can see my arrow, but maybe not, but the smallest smoke counter should be at least 2/3 of the room area that you want to clean. So because of this number here, the room area that this device can clean is about 222 square feet, which is not that big. So you need to be careful about making sure these numbers match up with the room that you want to be cleaning. So other important factors to do with this are things like noise. So these devices vary a lot in terms of how much noise they generate, how much energy they use, and of course, cost, and all the bells and whistles that I mentioned before. So the purpose of this review is actually not to tell you how to build a DIY air cleaner. That's not why we're here. Why we're here is to really take like a kind of deeper look at the evidence on air cleaner effectiveness, which is the CADR, and other important factors like cost effectiveness. So how much do you have to spend for each unit of clean air that you receive? The energy efficiency, which is, how many CADRs do you get per watt of energy used, and of course, noise. So the purpose of this review is really, it's to help decision makers, usually people in public health, although you may be in education or you may be a building administrator, where you're trying to develop your own strategy for using these DIY air cleaners. So you have a building to take care of, and you're maybe going to want to deploy a whole bunch of these. So this is kind of like giving you the evidence base for doing that. We also want to help people understand the use case, because how you use an air cleaner is going to vary depending on what kind of hazard you're dealing with. And we'll talk about that a little bit later. I also want to say, please download the full resource at our website. Hopefully, Kelsey or Leah, you can helpfully pop the link into the chat. I'm zooming through this today, like literally zooming and zooming. So please go, don't just trust the webinar, go to the paper and read the paper. It has a lot more of the nuance, and of course, all the papers that we reviewed. So methods wise, whenever NCCEH does an evidence review, and we have lots and lots on our website, we review various sources. This particular document looked at scholarly and gray literature, and you can see the full document for the full methods. The sources that I'm covering here, there was 20 different studies. 9 were peer-reviewed, 3 were preprints, and 8 were technical reports from trusted institutions like the EPA or public health institutions. And the document was also internally and externally reviewed. So I want to say thank you very much to Pat Gogan and Sarah Rumbold from Health Canada, who reviewed, and also Alison Savage from the EPA, who not only reviewed, but she also shared a matrix of just data that she had been collecting on air cleaners, which was a big help. And I also got Twitter reviewed yesterday, so that was fun. It was helpful. So what kind of air cleaners did I include in this review? I'm looking at 5 designs here in this paper, and they're basically different configurations, all made with the same materials. There are lots of other different kinds of air cleaner designs out there, but they tend to be more technical. Like they're a little bit, kind of engineering students having a good time on a Saturday, and they built an air cleaner. But these are the ones that are simplest, and they're meant to be deployed by the public. So in the paper, this is what we're calling a 1x1 air cleaner. So essentially you've got one 20 by 20 inch MERV filter, you've got one 20 by 20 inch box fan, you've got a cardboard shroud, and all that together will run you $50.49 Canadian from Canadian Tire before tax. So yes, for people in the United States, things are a lot more expensive here. So the air will flow through this way. So basically what you have is the filter is actually taped onto the back of the fan, and the air is pulled through the filter, then through the fan, then out the front. And you've got this shroud here on the front. One important thing, first of all, shout out to Molly Mastel, who took these photos for me. I really appreciate that. But what Molly noticed when she was building this sucker is that the controls were right here on the front of the fan, which made it kind of difficult to put the shroud on. And then also there was like an electrical cord coming out the back, which made it difficult to get the filter on flat. So you just have to make sure if this happens that you get all those gaps sealed, because you don't want the air bypassing. So this is what we're calling a 2x1, because it's got two filters and one fan and a shroud and these top and bottom plates. And when you put that all together, you get this thing here in the middle, which is also called a wedge design. And basically you just got to make sure those airflow direction lines line up, and that'll cost you about $66. A 3x2 design now has 3 filters, 2 fans, 2 shrouds and bottom plates, and that'll cost you $116. It's the most expensive design because of the extra fan. The air kind of flows in the 2 sides and the top, and then out through the fans, and you have cardboard plates on the bottom. The next design is a 4x1. You got 4 filters, 1 fan. That'll cost about $96.97 before tax. And it goes together like this in a cube with the fan pointing up, so that the air is being drawn in the sides and then coming right out the top. And this is what's commonly known as a Corsi-Rosenthal box. And there's cardboard panels on the bottom just to close it out. The last one is kind of a variation on that, where now you've got 5 filters and 1 fan. And you've got a filter actually on the bottom of the cube and some improvised legs just made out of the fan box. And yeah, so air is flowing through 5 panels on that and going out the top, but that'll cost $112.47 because these furnace filters they're cheap, but they're not cheap. So as a result of that, you have to kind of consider, well, with the 3x2 design, which has the fan, it's only a couple dollars more expensive than this, but because it's got an extra fan, it's actually going to move a lot more air and give you most likely a much higher clean air delivery rate. So we'll talk about that next. Okay, so here's a big table. I know people don't like big tables, but I gotta show it to you. So this is actually just an excerpt of what's in the paper. The paper has a much larger data table. These are only the studies that compare DIY filters or DIY air cleaners to commercial devices. So, and when you look at them, it's kind of hard to see it in the arrow work here. You can see that actually in these studies, so first of all, these 5 different studies, they actually use different methods to either measure or estimate CATR. So you can't really compare down the column. You can just kind of compare within the studies. But if you do that, you'll see that here, this 4x1 design created a much higher CATR than these 2 commercial units. This one was pretty similar. This holder paper, they did 3 different designs and they all did better than the commercial HEPA unit. This paper, they did 3 designs and they all did really good, especially this 3x2 design with the 2 fans. And that's just because 2 fans means a lot more air moving. And then down here, this is a 1x1 design and it did pretty good compared to the commercial HEPA units that they bought. They had 4 of those running. So in terms of cost per CATR, so how much money do you have to pay for the air that's getting cleaned? You can see really starkly that the DIY devices, everything is kind of below 36 cents. So you've got some here, this DIY device here is only 6 cents per CATR. 8 cents per cutter for this 3x2 because it creates such a high flow rate. Whereas the commercial air cleaners were kind of all above 65 cents per cutter. And some of them are really high. There's one here, it was $6.80 to clean that unit of air, where it would be per cubic foot per minute of air. So quite expensive for air cleaning. So the DIY air cleaners were also more energy efficient than I expected, which was a bit troubling because I thought that I kind of just assumed that the commercial air cleaners would be more energy efficient. I don't know why, but basically how we measure this is there's different thresholds for different devices at different clean air delivery rates. So for the highest one, so if you have a clean air delivery rate of 150 cubic feet per minute, then you need to be providing at least 2.9 cutters per watt of energy used in order to be considered energy efficient. And at that flow rate, most of them did. This one did not. These two did. This was a 2x1 and a 4x1 design. And this 1x1 design down here did actually suspiciously good. So you can see that they were actually more energy efficient than expected. And finally, noise. Not everybody measured noise, but you can see that the DIY devices did tend to be a bit noisier. So they're kind of within like 10 decibels noisier than the commercial units, but the commercial units were also kind of noisy. So for reference, when you move from 50 to 70 decibels, that's kind of like a quiet to a loud conversation. And so that might not seem like much, but it could actually be pretty disruptive in what's supposed to be a quiet environment, especially if you're somebody who's already hard of hearing. That could actually be really problematic for you. So in terms of these DIY devices in the real world, there was only 5 studies that did real world deployments. And unfortunately, the longest one of those, most of them were very short trials. The longest one was 6 months, which was, pretty great. And what they saw was, it was in classrooms. And what they saw was that the filter efficiency dropped from 92 to about 77%, but it was still working pretty well. And that's important. But you also have to note that there were no smoke events during that time. So if there had been a wildfire event, that may not have been the case. This Gasparini study was, I think it's still a preprint, but it was interesting because they did their deployment, but they also did a little bit of modeling to figure out, kind of answer the question of how well is this mixing? And I mean, it's not mixing well, but you can see they've got 2 air cleaners in each corner and they're getting a little bit of mixing across the room, but mixing is going to be an issue for any kind of air cleaner, commercial or DIY, and you have to be conscious of where it's being placed. Is the air going to be able to flow to it and around it? And that can be really challenging if you have a lot of furniture or like cubicle walls or stuff like that. So these studies did not look at user engagement. Okay, so they didn't really like go to the users, the occupants of the room, and talk to them about how did you feel about this air cleaner? But even though they didn't do that, they did make note that people did not like the noise. So that there was some noise problems, especially like if it was at the high fan speed. So noise is a problem. All right, so at this point, I'd like to ask folks when you're going through this presentation, where are you thinking about these DIY air cleaners being deployed? Home, schools. I like to see schools, multiple different spaces. That's great. A lot of people thinking about their homes here. Awesome. Great. So you can see, yeah, we're mostly thinking about home stuff, a bit of school, bit of office, bit of clinic, and then multiple different spaces. So those are that's a more complicated situation here. All right, cool, thank you. So that moves us into our next slide, which is how we choose the right design for the space. And unfortunately, there's no easy advice for this, but I'll just kind of tell you like how the factors change. One important thing to remember is that the cutter and the cost increase together with the number, thickness, and MERV rating of the filters. So The more, if you're going to build a vise with more filters, it's going to cost more money. If you make the filters thicker, it's going to cost more money, but it's also going to give you a higher cleaner delivery rate. If you use the design with more fans, the more fans is going to really increase the cutter. So that's could be important in some situations. So if you're thinking about doing this for, a situation where you have an office or a school and you're thinking you're going to have to deploy a whole bunch of these, then it's really important to do some math and figure out kind of where the sweet spot is for the cost angle of it. And, build some prototypes to understand, like, how would they fit into the space? Are they easy to knock over? Just kind of like before you commit to buying a whole bunch of these materials. So noise also depends on, obviously, the fan type. Different fans are noisier than others. You can buy more expensive fans that are quieter. You can also modulate the fan speed and obviously the number of fans that you have in the room. So you might have one of those 3x2 designs, or you might have multiple 1x1 designs, and all those fans are going to add to the decibels in the room. So the number of devices, as I just said, depending on the room size and the cost of the materials, if you have a big room, you're probably going to need multiple devices. And depending on kind of like cost of materials and stuff, sometimes it can be cheaper and better to have several of the 1x1s rather than one of the bigger, like the Corsi Rosenthal or the 3x2. It kind of just depends on the space and the cost of materials. Space-wise, the cube designs take up a bit more space. So that might be a consideration if you've got a really crowded area. And finally, occupants. We're going to talk about occupants, but will the occupants use it correctly? And that's not a given. So in terms of building it right, there's I can provide you with links to how to build these things. And there's lots of great tutorials online, on YouTube, on Twitter, places like that. But the three really important things that I should bring up are, first of all, using a fan shroud. So the fan shroud is this cardboard thing here on the front face of the fan. And what this is doing is preventing re-entrainment of the air that you already pushed through. So as you kind of move from the center of the fan out, you'll see that, like, if you go like this, the airspeed starts to increase. And this is kind of like where the peak airspeed is. And then as you move towards the corner where the gap is, the airspeed drops and then reverses. So you're actually sucking in air at the corners, air that you already pushed out. So that's just not efficient. And so putting one of these cardboard things on there prevents that from happening. And in the various studies that have done this, they've shown that it really increases the efficiency by increasing the cutter. So this holder paper, which was just out, like, I think November or December, it's a really excellent paper. I really recommend people read it. They saw a 40% increase in the clean air delivery rate just by having that shroud on there. So that's a really important thing to do. Don't omit it. The other important thing is to use a newer fan with a safety fuse that has been certified by a safety agency or electrical safety agency. So I'll talk a bit more of that in the next slide. And also just to seal the gaps really well, because you want the unit, first of all, not to bypass air. You want the air to be sucked through the filter, not sucked through the cracks, because then it's not getting filtered. So you want that to be well sealed off, but you also want it to be stable, especially if you're building, it's one of the big cube designs that the filters are the structure. So if you don't tape that together well, then you could have, structural failure. And finally, just make sure the flow, the direction of airflow is correct. So the filter has a little arrow on it. Air only goes through that filter in one way. And you got to make sure that lines up with the direction of airflow on the fan. And I hope here one of my dear colleagues will drop in a link to the EPA infographic on how to build a 1x1 design, just as a reference. But as I say, there's many guidances out there for building these things. So safety. There have been always concerns about these DIY air cleaners overheating or causing a fire. And the reason why is that you're taking a fan and you're strapping stuff onto it, you're obstructing the flow of air, and it's not meant to be used that way. And so, could it start a fire? So this group here, Davis and Black, they did a study called the Wildfire Safety Research Evaluation of DIY Air Filtration Report, which was done, I think, in conjunction with the EPA. And they basically tried to light fans on fire. So they did a bunch of different studies, or a bunch of different trials with like fans that variously obstructed or with preloaded filters loaded with like smoke or dust. And the one that I'm showing you here in this picture is the most extreme one, where basically they laid it face down on the floor, and then they also taped plastic over the back so it was totally obstructed, and they ran it for 7 hours. And then they used these little wires here. They're measuring temperature on the handles, on the controls, on the fan motor, different parts of the machine. And what they found was that it did definitely heat up, but there was not to the point where there would be considered a risk of burns or ignition. Okay. That said, they did this at 20 degrees Celsius. So if you had the same fan running like that in an apartment, in a condo building, and it's 40 degrees in there, it might not be the same situation. But just generally, the kind of public health agencies strongly recommend using a newer fan with a safety fuse so that if it does overheat, it would shut off. Okay, so the other thing to note is that a high fan speed is not necessarily the best. If it's running at high speed, it's more noisy, it's more drafty, and it may even be kicking up particles as it's pushing the air out. So some of those particles will get, drawn back into the air cleaner and filtered out, but other ones will just be floating around in your air then. So you've not had the best effect on your indoor air quality. Okay, so knowing the hazard you are addressing. This is really important because different kinds of situations, exposures require a different response. So the first one I like kind of going to contrast to here is smoke. So smoke is coming from like a wildfire, for example. It's coming from outside the room. It's infiltrating through all the different little cracks in the building envelope. And so it's creating kind of like a more diffuse exposure inside. So what you do in that case is, first of all, you close all the windows. You close the damper for your ventilation system so you're not bringing unfiltered air in. And then you turn your air cleaner on. So you're basically trying to cut your space off from the outside and just clean the air that's inside the room. And of course, you have to change the filter more often if there is, if you notice it becoming really soiled. In terms of a virus, however, that's a totally different situation. So now the source of exposure is inside the room. And you could argue this about whether this is really a point source or not, but it's coming from a person, or it might be coming from multiple people. So the exposure in the room is not, it's like less homogeneous rather than more homogeneous, I guess. And so the way to deal with this is to increase the ventilation. So you're trying to get as much fresh outdoor air in the space as possible while also running the air cleaner. So you're trying to increase your total air changes per hour, both through your ventilation system and by supplementation with this filtered air from the device. And then you might have continuous versus episodic exposures where you've got, if you're living in a moldy house and you know that it's moldy, you should probably do something about that. But say you can't for whatever reason, or you're working on it, then you need to run your air cleaner all the time because the mold is continually being produced and released and releasing spores. So you need to be continuously using this. Whereas something episodic might be, Christmas dinner, we're going to turn the air cleaner on while my sick relatives are here, my unknown, not knowing if my relatives are sick or not. So the other thing that came up a lot in this evidence review was the importance of maintaining the filters. So it's hard to give advice on this without a way to measure CADR, which we're actually going to talk about next. You just don't want to get to the point where your filters get so obstructed that you're now not getting a good clean air delivery rate anymore. So this is a graph from that Holder paper that I just mentioned, and hopefully Kelsey can drop the link. But basically, this is the kind of base case that they did here. This is you can't see my arrow. This is a 1x1 design with just a MERV 13 filter. And they did a lot of different things to this air cleaner. They put it in the corner. They use bungee cords to fix it. They increased the filter size to a 4-inch. You can see that a CADR goes way up. They increased it to decreased it to a MERV 11, so the CADR goes down. But then they did some loading with smoke and dust. And you can see that even loading just a little bit of smoke on that just totally killed the clean air delivery rate. So this is not a situation you want to be in. And when you're changing those filters, you have to remember that they're contaminated with various contaminants, like whatever came out of the room air. So it should be treated carefully, like being bagged and, using a mask and gloves to change it. Okay, get up there. Oh, just had a couple of arrows there, I forgot. Alrighty. All right, so how do we know it's working? This is the key problem. So if you read the full paper, you'll see that there was a couple of studies where they really made an effort to develop some low-cost methods to actually either measure or estimate Cotter, which is great. The only problem is they still require a little bit of technical proficiency, and it's something where you kind of have to like set up an experimental chamber and test it. So you can't really like keep testing it over time. You would have to like pull the air cleaners out of the room and then like set up your experimental chamber again, test them again, and so on. So while writing this paper, we had a lot of discussion about this. What would be the kind of the best approach to recommend? And that would be using low-cost PM sensors. So these are little devices. This one is just like a little handheld device. And basically what they do is they just measure the particulate matter in the air at different size fractions. And if you have two of them, what you can do, because PM particulate matter is continuously generated both indoors and outdoors, and those two sources are kind of like connected to each other. The outdoor PM is going to be affecting indoor PM throughout the day. So what you can do is you can use two of these sensors. You can put one outside to keep track of what's going on outside, and then you put another one inside. And when you do that, you can see whether or not the indoor levels are dropping relative to the outdoor levels. So there's three main benefits of that. First of all, it's just obviously much more straightforward to work with than trying to measure Cotter, which takes a little bit of knowledge. It also it lets you understand the contribution of various sources inside. So say you're cooking or you have a cooking inside, that will cause the indoor PM to go up. Or if you have really smoky conditions outside, you'll see the outdoor PM go up and then the indoor PM will go up. It's also good because it's a quick check. You can repeatedly come back and you can check the room relative to the outside various times. So it's not like you test the machine once and then it's done. You can keep coming back and testing it, and you'll see maybe, oh, my Cotter or my the PM levels drop really quickly when I started using this device, but 3 months in, I'm not actually seeing a big decrease in PM in this room anymore. So what does that mean? That means, well, maybe conditions changed outside or your filter's getting clogged up, and so you need to do something about that to be able to actually remove the PM. So PM sensors are way beyond what I can discuss in this particular talk. So I'm going to point you to the EPA's website, which has a whole big table on evaluating emerging air sensor performance. And where basically they just go through a bunch of different PM sensors, and they've got a whole bunch of different types of sensors on the page actually. And they link to all their various documents where they evaluate those. And this is really useful for when you're in the point that you need to select one. I'll also say, oh yeah, I'm not endorsing this. This Met one is up here because it's a cute little sensor, but I am not endorsing this in any way. The other resource that the EPA has is this newly updated enhanced air sensor guidebook. So this is really kind of like the Bible if you want to start getting into PM sensors. Not only does it start out in the beginning, really giving a much better than I just did, review of outdoor and indoor air quality and PM generation and how they're connected. It also helps you understand how sensors work, understand like physically how they work and how to use them, but also selecting a sensor that's appropriate for your project, how to collect data and analyze data, store data, more importantly, how to design a monitoring campaign that has some of that quality assurance, quality control stuff built in so that you're not, making a hash of it, and then how to communicate and act on your results. So yeah, I highly recommend this is a must read if you're going to get into PM sensors or any kind of air sensor to do community science. Okay, so pesky limitations. The most important one that we need to be, if we're telling people how, when, whether to use these devices, we need to be really clear about this limitation, which is that DIY air cleaners are not purifiers. We have to stop using that word because they don't remove other very dangerous indoor pollutants. So example of those are radon specifically and carbon monoxide, which kill a lot of people. In Canada, every year, 3,000 people die because of radon-related lung cancer, and that's around 21,000 people a year in the US. So, these are very serious indoor air pollutants. Carbon monoxide kills about 300 people every year in Canada, And I think it's about 430 or 450 every year in the US, where it's not quite as cold as it is here. But also those are like the two most kind of deadly ones, but volatile organic compounds can be really nasty respiratory irritants, and some of them are carcinogens. CO2 affects people in terms of like stuffiness and odor, or like kind of like feeling stuffy, feeling uncomfortable, fatigue, headaches, stuff like that as well. So DIY air cleaners will do nothing for these. So it's really important that we can build DIY air cleaners for people and get them to use them, but at the same time take the opportunity to talk about this other stuff. So you want to use a DIY air cleaner? Great. Have you tested your home for radon? That would be a really good thing to do. So we want to be very clear that this is not a solve-all situation. Those DIY air cleaners do not replace the need for ventilation. So I know during the pandemic, there's a lot of times where people will be like, I want to run my business, but I've got no ventilation whatsoever. Can I just put an air cleaner in there and that's good enough? And the answer to that is, well, no, you need to have proper ventilation in your space, and the air cleaner is a supplement to that. As I've mentioned several times already, use is going to vary depending on what hazard you're dealing with. So it's really important to make sure that your occupants, your users, are informed about what to do and why, and how to take care of the device. Okay, another pesky limitation has to do with humans, and the fact that you really cannot expect the occupants to play ball with this DIY air cleaner thing. So just recently in September, I finished a big review that was all about manual ventilation, so opening and closing windows in schools, and whether or not having a CO2 sensor in the classroom helped the teachers and students refine their ventilation behavior. So it's just trying to understand, like, does it make any sense to buy people CO2 sensors? Will they follow them? Will it actually make a difference? And in actual fact, it was very hard to answer that question because the studies did not really collect much information on user engagement, or like understand how were they engaging with the CO2 sensor. But generally, it didn't seem like the CO2 sensors had a big effect. And the reason why, and the authors of the various studies noted this, was that it seemed to really depend on occupant willingness and engagement. So some of the teachers were really into it, and the students were really engaged, and that worked great. And other students and teachers couldn't be bothered. And so that's going to be the same issue with DIY air cleaners, is that if you want to use these, say in a school or a long-term care home or an office, you have to educate the users first, get people on board, explain what the benefits are, explain how to take care of it, and just try to engage them in the process so that they will continue the behavior over time, and the maintenance of the device as well. And it's important to recognize that in some cases, it just won't be fit for all spaces. So I could see a situation where you've got a daycare with really little kids around, not really sure you want to have an air cleaner with an exposed dirty filter where they can get their little fingers in it, right? These are considerations you have to think about the users in the room and whether or not they're going to be able to take care of this thing. Okay. So the last pesky limitation is something that has to do with just kind of ventilation and air cleaning generally, which is that, as I've mentioned, the pathogen in the room, so the indoor source of exposure is a point source. There's a person or multiple people in there who are breathing out this pathogen and filling the space. And this figure is one that I borrowed from a paper that came out in 2020. The reference is there below, but I've kind of modified it to make my point, which is that when you are in the room with a person emitting this pathogen, emitting this pollutant, the benefit of the ventilation or the air cleaning is very dependent on your relative position to the source of the pathogen and the source of the clean air. So in this picture, if you're this guy over here, I don't know if you can see my arrow, but the guy on the right, he's got a lot of protection here because the windows are open. There's a ventilation system going. There's some air cleaning. There's a portable air cleaner. There's a UV lamp. So maybe all these things working together are going to help him on the right there avoid infection. But if you're this guy, all those different air cleaning and ventilation technologies are not going to make any difference for you whatsoever. So there's really not, like, it's just kind of things are happening on different time scales. So these two people close together are exchanging thousands of particles per second, whereas the room is turning over at a much slower rate. So it's really important to remember that these air cleaners are going to reduce the overall exposure, but not equally for everyone. And so some people may avoid infections. Some people may have less severe infections. Other people may not have any effect at all. So it's not about overselling the benefits of these air cleaners. They're good to have, but you still need to follow those other critical public health measures. All right, so I've left lots and lots of time for questions, but just to sum up, in a controlled environment where we test DIY air cleaners, so in these chamber studies, we can say that the DIY air cleaners with MERV 13 filters performed quite comparably compared to the commercial devices in reducing indoor particulate matter. And although there was less field data to draw from, the data suggests a need for kind of a quality assurance method and maybe some thoughtfulness about how to engage the occupants about their use. And it's important finally to remember that no portable air cleaner is a permanent solution for bad ventilation, but rather a supplement or an interim measure. And we need to always be pushing as public health people, pushing to make sure that our rampant indoor air quality problems are solved the right way and for everybody, not just for the people who can afford it. Alrighty, so thanks very much. And I think we have time for some questions.